no problem.
Okay, sir. And there is no question in the discussion forum.
Okay. So anyone is there here who is
Sir?
anyone is there from participants?
Uh, in Zoom, there are two persons. They are your TS or what, sir?
Satish is my TA.
Okay, then other person is, I think, is a participant.
Oh, okay. Nachiket, are you able to hear us?
Nachiket, if you are in online, please respond. Okay, sir, we'll wait for some time.
Sure, sure, yeah, sure.
Or else, if we give permission, we can mind it.
Yes, Professor, I can hear you. Yes.
Yes, please ask your doubts or query with faculty.
Yeah, do you have any questions you want to ask?
Actually, I just joined the session to have a look at what is going on, like in discussion. So I don't have any doubt as in particular related to this course.
Okay.
Okay, sir, then we'll wait for 5 to 7 minutes.
Sure, yeah, sure. No problem.
Maximum till 10:40 we can wait. So if
Yeah,
at all there is no participants with no questions, then if we give permission, we'll do the mind.
Sure, yeah.
Okay, sir. Thank you, sir.
Yeah, thanks.
Excuse me, Professor.
Yeah, yes.
If you don't mind, can I ask a question? I mean, not exactly related to this course, but I mean in representation theory somewhere around.
You like general representation theory?
Representation theory of compact groups, compactly groups.
Okay, that is equivalent to actually representation theory of semi-simple algebras, na?
Yes, sir. Yes, sir. Exactly. Yes.
Okay, yeah. What do you want to ask?
So, sir, actually, I was reading or I was studying Peter-Weyl theorems I mean in harmonic analysis for compact Lie groups, and I mean there are quite there are rigorous proofs available for the statements of the Peter-Weyl theorem that the matrix coefficient functions are dense in the L2G space, and then um, they give the canonical decomposition of L2G as a G cross G module. So in some places they understand Peter-Weyl theorem as decomposition over G action, and in some places they consider the decomposition over G cross G action on L2G. but I mean, I was totally lost in all the rigorous methods involved, and I was not able to catch what is really the soul of this Peter-Weil theorem. So if you could comment a bit on, I mean, what is really to be taken from this theorem, it would be helpful for me.
Okay, so I will actually tell from my understanding. So,
Yes, yes,
so you are interested in, let us say, kind of constructing actually all representation at once. Okay.
yes, sir.
So if you are interested, let's say, constructing all irreducible finite dimensional representations.
Yes, sir.
So, and of course, this L2 space is also somewhat very interesting space studied from analysis point of view.
Yes,
Okay.
yes,
So you look at the natural action of G on L2 space, and then it is infinite dimensional space. You
yes,
just
sir.
ask this very basic question that we ask every time in representation theory. Okay. So what are all the fundamental questions in representation theory? If you have a representation, so then can you write down that as somewhat smaller representations which can be understood properly? Okay.
Yes, yes,
So that is the first question in some sense. So when they are writing it as using G action, that's what they are telling you. Okay, how to decompose L2 space into G representations. Okay,
okay, sir.
I guess when they are writing it as G cross G module, then so what will be like? So basically, each irreducible representation will occur with some multiplicity. Even that multiplicity space you can actually kind of hear because if you think it as a bimodule, then you will be able to actually say like much more information about that multiplicity instead of
Okay,
giving like some abstract thing. So
okay.
I guess similar results are there. Like so, Satish actually make like Satish. You remember anything like for the finite dimensional algebras?
Mm, no, sir, I don't. I don't remember.
You don't remember anything like so sure while duality is one such thing, but there you are actually using two different algebras.
Where, sir?
Sure while duality.
Okay, Scarwile. Okay, okay.
Yeah, sure while duality actually you are actually using two different algebras, like GLN and the group algebra of the symmetric group. Okay. So if you think about it like so if you think that has actually a bimodule, then the decomposition becomes much more precise. Na? So maybe like, so have you seen Shurwal duality?
No, no, sir. No, sir. Not yet, sir.
Yeah, maybe like you should actually read bit about it because
Okay.
if you understand compact group representation theory,
Yes.
that means you have some idea about symmetric group. Na?
Yes, yes, sir. Yes, sir.
Yeah, then like, so basically like, you know, the symmetric group acts on this natural representation Cn, okay, by permuting
Yes.
the coordinates.
Yes. Yes.
And then that Cn can be treated as a natural representation for GLM. Okay.
Yes, sir.
So I guess okay, in Shurwal duality, you will be using actually different thing. So you take V to be Cn and look at actually K tensor products of that Cn. Then you can make Sk act on that. So that is how you are bringing in GLN and symmetric group Sk. So then you want to understand, okay, you take this tensor product, K copies of Cn,
Yes, sir.
okay. So then as a GLN module, it will decompose into some irreducibles, okay. And as well as a Sk module, it will decompose as some irreducibles.
Okay, sir.
So, but if you actually think about this as a bimodule, okay, like GLN cross Sk module, so then it will have a like very nice decomposition that will actually tell about the multiplicity of irreducible components that occur. Like as GLN module as well as SK module. Okay, there will be some duality that you can see.
I
So,
see.
so this is where like you can see that like taking product of two algebras and looking at as bi-module. So you will have much more understanding of this multiplicity in terms of some other space. Okay.
I see.
I
Okay.
guess the Peter-Weyl theorem that you are actually mentioning two
Yes.
different ways. So if you think in terms of G cross G, maybe that is what you will be getting.
Okay, sir.
So
So
if
it,
you are thinking it as a G module, then you decompose it as some direct sum of irreducibles with some multiplicity.
yes, sir.
But that multiplicity also you want to understand
Yes, sir. Yes, sir.
what it is and so on. So then if you think it as G cross G module,
Yes,
so
sir.
then what will happen? That same like it will decompose it as again like some of these G cross G modules. But there you will see, I guess the correct thing will be the irreducible module tensor. It's a dual,
Yes, exactly. E pi star tensor E pi, where
yeah.
E pi is the
So, but
isotop.
if you think it as a G representation, you know that that irreducible module occurs with the dimension of that irreducible module times that kind of
Yes.
that many
Yes.
multiplicities. But
Yes.
when you
Yes.
are thinking it as G cross G module, so then you identify like why that multiplicity exactly appears. So that's entire space decomposes into some natural way so that you are actually getting that multiplicity for some reasons. So that multiplicity is not coming for free. Okay.
Okay,
It's
sir.
not some coincidence or anything. That has a deep meaning when you think it as a G cross G module.
Okay, sir. I
So
see.
that is what like you compare sure while duality, then that it's almost kind of similar statement.
Okay,
Because
sir.
here you are looking at only one, let's say one algebra.
Yes.
Like
Yes.
you can put it in the Lie algebra language, but there you can actually see the two algebras are involved, but one space you are trying to decompose it into like two different ways.
Okay, sir.
Actually, three different ways there. Because as GLN module you want to decompose, as SK module you want to decompose. Now
And
GLN
here
plus
process.
SK module you want to decompose.
Yes. Yes. I see. Thank you very much.
Yeah, there are many good references for this. I guess very short reference will be like uh,
Goldman Harris.
no, there is this ISI. Sitaram has some book on this. Chandrasekhar has actually one very nice on. It's called topological groups. I guess it's a TA for notes.
Yes.
Chandrasekhar. Okay, sir.
Yeah, it's a conscious, very short way of proving Peter Algebra.
Okay, sir.
Chandrasekhar. It's a TA for lecture notes.
Okay, sir.
Maybe that you can actually.
Right now, I was following compact Lie groups by Mark Stepansky.
Okay.
So I was reading from that, and
Yeah, this book is very short book. It's called A Course on Topological Groups. It starts with the topological groups and then builds Peter Algebra
okay, sir. Okay.
by Chandrasekhar. You have any other questions?
Yes, sir. One more question. So let's say that we have a non-abelian group, and
Okay.
then we consider the space of all continuous functions on this non-abelian group,
Okay.
and then we take the spectrum of this algebra of functions.
Mm-hmm.
But I mean, I have read at some places that this character space may not have enough elements, so to say. Uh, but I'm not sure what it means that uh, I mean, if let's say there is a normal compact Hausdorff space X, and then you consider. So I'm talking in terms of Gelfand-Naimark.
Mhm.
So for the pointwise multiplication, the CX is an abelian algebra, excellent, and the character space has this maximal ideal identification, and everything is fine. But then when we, let's say now we replace this compact topological space Hausdorff space X with a Hausdorff topological group G, and then I construct functions on this group, and I define the multiplication between them, but then the group is now non-abelian, and so this function algebra will be also it's non-abelian algebra. And now what changes when we consider the character space of this algebra? I mean, what kind of correspondences can we still make about from with the original group G and the ideals in CG?
Okay, I haven't looked at all these things. So, but I can actually tell you whom you should talk with. So, you know E.K. Narayanan from our department, IAC.
E.K. Narayan, yes sir, yes sir.
Yeah, yeah. So, he will be the correct person to talk with actually these things. So, he has done some work on all this stuff, non-abelian groups actually. Anyway, he does harmonic analysis as well as representation theory of Lie groups. Okay.
Okay sir.
So he may know better than me.
Yeah.
You can write to him, not a problem.
Okay, yeah, because I'm not a student at IISc. I am.
No,
So
no,
that,
but you can write to him. He is very friendly guy.
okay, sir.
He will, yeah, he will reply. No problem. If you want, you can CC me, not a problem.
Okay, sure.
Yeah. Where are you from?
Sir, actually, I am from Indore, but I am doing my master's in mathematical physics from University of Wrocław in Poland.
Oh, okay, nice.
So right, actually, right now I'm working on my master's thesis, and it is in this area of non-commutative geometry and
Mm-hmm.
quantum groups, but from functional analysis perspective.
Oh,
So
okay. Oh.
so that's why I was dealing with all of these things. That's what I was.
Yeah, so these topics, like another person will be like Ishan Patri from ISI Delhi. So he works on these things. And Partha, so Satish, you know his full name, na? Partha Chakraborty.
Yeah, Parthasari Chakraborty, right?
Partha
ISI
Sarma,
Kolkata.
ISI Kolkata.
Hmm.
So they are actually experts in this non-commutative geometry.
Okay.
So they know better than yeah, me. Like I am interested in quantum groups that comes from Lie theory. Yeah, which is algebraically motivated.
Yeah,
Not,
like from Hopf algebras. Yeah,
yeah, Hopf algebra structure.
I see. So
But
I
these
was
basic questions, Narayanan can answer, not a problem.
uh-huh.
Like about anything related to harmonic analysis and representation theory of
Yeah.
these non-abelian groups. So because he has done some work on those things.
Okay. Also, if you have 2 more minutes, uh, so in terms of Hopf algebras, when we try to understand quantum groups, uh, there is a duality which I have studied about that. One is we quantize the universal enveloping algebra of a Lie algebra, and the other way is to quantize, or let's say deform the matrix coefficient functions of uh,
Matrix coefficient functions of.
so let's say we have this matrix group, let's say SU2,
Okay.
and then we do a Q deformation of the matrix coefficient functions.
Okay.
So now these are non-commutative, and they say that there is a duality between this as well, from the approach from quantizing the universal enveloping algebra and deforming the algebra of matrix coefficient functions of these SU2 matrices, like for example.
Oh, okay.
So could you tell me something about this, because it is not very clear to me. I mean, I have this formula in front of me that I have seen, but then still, I mean, what's the essence of this? There
So
there are a lot of composition of maps which I can see in front of me, but I mean, how to make sense of this?
Okay, like from this perspective, I never looked at it actually. So what do you mean by the duality? Like it is happening at the level of representation space, or
At the level
uh,
of categories, I
sorry?
think. At the level of categories, I think. So in
Oh, you want to say that the category of representations will be equal or
yes,
something?
yes, the morphisms are reversed, and you are now in the dual spaces at both. So the category duality, conventional, which we talk about.
No, okay, sorry, I haven't looked at it from this perspective. Like usually, yeah, purely from algebraic point of view, there are things that we try to study the sure while duality generalizations actually. There is a
Okay.
quantum sure while duality and so on. But
Okay.
what you are asking is that Lie group and Lie algebras correspondence, nah?
Yes, yes,
How
exactly. Yes, yes, Professor.
how
Yes,
that is extended to the
yes. So we can
yeah,
quantify
because
the level of Lie group, and we
I never looked at
yeah.
the quantum group definition from Lie group's point of view. It
Okay.
is always like because you start with the same presentation and then like
Uh,
from that it is easy to write down the this presentation of these quantum groups. Okay,
yes,
so
yes.
only from that point of view I have studied.
Okay, Professor. Okay.
Yeah, so yeah, I honestly don't know like this correspondence, but maybe I can look at it and then maybe like share some.
Yeah, sure.
Later.
Can I email you after this?
Sure,
And
sure, sure. Yeah, no problem. Yeah, you can write your questions. You can mail me. Yeah.
yes,
And the question that you want to ask now also you can ask and then CC me. No issue.
yeah, sure.
Yeah.
Can we also generalize this Pontryagin duality? Uh,
What is that?
the Pontryagin duality. About the okay, but it is again in this topological group sense. Okay. Okay, maybe I'll refine a bit more my question and then email you.
Sure, sure. Yes.
Okay, thank you for your time. Thank you.
Yeah. Okay. Okay, looks like no one else is joining. You are done with all your questions?
Yes, Professor.
Okay. Yeah, okay.
Okay, sir. Then we'll.
Maybe Naveen, yeah, if you want, we can close this session because I don't
Okay,
think
sir.
anyone else joined.
Okay, sir.
Should we wait because we waited already 20 more than 25.
Yeah. Okay, sir. Then
Yeah, we
we'll
can
wind up
close
the
the
session.
session. Yeah. Please,
Okay, sir.
Nachiket,
Thank you, sir.
you can mail me, okay?
Yes, definitely, Professor.
Sure, yes. Okay.
Thank you, Professor.
Okay. Bye-bye.
Okay, sir. Thank you, sir.
Yeah.